going to take a peek today at simple probability, which I would certainly hope sometime within your mathematical time that you have seen. So hopefully then as we start to build on this and get into our other types, like the compound, the theoretical, the conditional, and kind of start to build on this, that it kind of starts to come together for you. So again, just in general, probability is just a chance that something happens. Okay? Most of the time, at least within the mathematical form here, we normally will do it as a simplified fraction. But doing it the other way as a percentage or as a decimal between 0 and 1, 0 meaning there's no probability, 1 meaning there's 100% probability that's going to happen. Okay? So, probability of rain today, 1 out of 4, which is, if I do 1 out of 4 in the calculator, is 0.25, and the percentage would be 25%. So when I read that, P rain, I'm not going to say P rain equals 1/4. I'm going to say the probability of rain is, or is approximately, that value. Okay? So the probability of whatever event it is. So when we do the probability, normally we chat about something, whether it's experimental, which we kind of deal with more of the time, so we don't give it its own notes like we do some of the other things. And theoretical, which we're going to talk about a little bit more a little bit later in the week, which is, here's what I think should happen. Like if I have a die and I roll it, getting any of the numbers approximately is 1 out of 6, because, well, there's pretty close to an equal chance that all those are going to happen. So in general, what we're interested in, or sometimes what I like to call the number of successes, okay? How many times do I get what I want out of the total number of things that can happen? And that's what probability in general is going to be. However, what we tend to deal with most often in the probability realm is experimental. Not this should happen, but this is exactly how it works. So we're going to actually use data, something that we've actually done or something that we've actually seen happen already. So in experimental, it's the number of times that the event I'm looking for occurs, okay, over the number of times that I do the experiment. And it may not necessarily end up being the same as what it would be theoretically. If I roll a die 6 times, I'm not going to get each number 1, 2, 3, 4, 5, 6 every single time I would do that. Sometimes I may get more 3s, sometimes I may get no 3s. So that's kind of our difference in theoretical and experimental, which is what we're going to discuss right here. So I take a peek. I go, okay, researchers find an experimental drug improved the condition of 340 out of 400 patients who were treated with it. What's the probability that it will help the other patients based on this data? So 340 out of the 400 were helped. So again, that's my success. That's my total. So then I just do my successes over my total. 340 divided by 400, and I always reduce the fraction as far as I can. And like I said, unless you see something differently on a worksheet, typically you're going to see the solutions that I put out there in a fractional form like this. However, it wouldn't be correct if you did it with the decimal or with the percentage on that. Okay? So just to give you, again, a heads up, most of the answers you're going to see out of me are going to look like this. Just correct. Even though if you do the decimal, it doesn't mean it's wrong. All right. Now, this is going to be just a little bit of background into theoretical. Like I said, we'll delve a little bit deeper into this as the unit goes on. Theoretical means we can do the calculation of the probability without actually doing an experiment. You know, well, how many times, would you figure you're going to get 6 if you rolled the die 10 times? But we're not actually going to roll the die 10 times. So the number of outcomes that would happen in event E versus the total number of possible. So just a slight difference. Okay? So here, we go to an event that has a door prize. There's 150 people who each placed a ticket in a hat. The tickets are mixed, a single ticket's drawn. What's the probability you're going to win? Well, there's 150 people. I'm one of the 150. So 1 out of 150. And again, leave it as a fraction. I can go to decimals and kind of work it that way. Now, maybe, okay, in reality, You don't know this. Maybe when you think you put your ticket in, somebody's taking them out, and there's only like a 1 in 50 chance, or maybe your chance is 0 because your ticket got taken out, but we don't know. But theoretically, you would have an equal chance as everyone else does. So, you spin a spinner with 5 equal sections, but we're not actually doing it. Numbered 1 through 5, find each probability. So if each of them are equal sections, I have an equal probability of getting each of those 5 values. So my probability of getting an odd number, yep, there's 3 of them, so it would be 3 out of 5. Probability out of even is 2 out of 5, because if you think about it, if you take all the odds and all the evens, you're covering everything, and 3/5 plus 2/5 is 5/5, or 1, which would give me a 100% chance of that happening. Okay? C, now this one's a little bit, we might have to think a little bit more on this one. Probability of not a factor of 5.
It would be 3, right? 3 out of 5?
I don't know. What are the factors of 5 that are listed?
1 and 5.
Nice, okay. Well, never mind. I shortchanged some of you. Okay? Because my non-factors of 5, like was just mentioned, would be 2, 3, and 4, because 1 and 5 are both factors of 5. So 3 out of 5 would be the probability of not spinning a factor of 5. And again, especially if you actually were paying attention, looked down below and saw the answers right below there. But again, she's like, what?
Where? I don't even see it.
Solutions. The answers actually were right below, but I wasn't going to mention that. So, now some of you may, now that you notice that, be like, well, wait a minute. Why did you write 1 minus 2/5 down here? Because another way that you can do this probability, if you get the word not in there, is to take the total probability, which is always 1. There's always, if we take all of the events into consideration, everything's going to happen in one way or another. And you subtract the factors of 5. So you don't do the not, you do the opposite part. Well, these are the factors of 5. So if I subtract them, that also would get me to the answer. Or you can just say, well, if it's not, I'm just going to take the ones that are not. Why would I do that? It just depends on the situation, but they both will get me to the right answer. Because if I take 1 and I give it a common denominator, it would be 5 over 5, right, minus 2 over 5. And that's where the 3/5 would come from. So again, that kind of goes along with this last part down on the bottom. But again, you always have a choice with this type of problem. Okay, an event does not happen, sort of like we had in number C, or letter C. It's not a number. Okay, so they're complementary events, because if you take the part that doesn't happen plus the part that does, it equals 1, or the entire event, 100%. So for instance, if the probability that a couple that has 5 children will have all girls is 1 in 32. You're like, wait a minute, how's that true? Okay, let me delve into this for a minute. Each time you have a child, what are the options? Boy or girl. So each time you have a 1 out of 2 chance that you're going to have a girl. And if you have 5 kids, that particular probability has happened 5 times. And it just so happens each time you've gotten the girl half. So if you multiply all those together, 4, 8, 16, that's where the 1 out of 32 is coming from. That's called compound probability, and that's something also we'll be discussing in future lessons. So if the probability they're going to have 5 children that are all girls, Lord help them, is 1 out of 32, what's the chance that you would have at least 1 boy in that? So, since the opposite of having all girls would have to mean you have at least 1 boy in there, then you could take the total 1, subtract the probability of all girls, which we just said was 1 out of 32, which gets me 31 out of 32. Or you could say, well, if the probability of that happening is 1 out of 32, I wonder how many are left. 31. So again, you don't have to do it this way. It's just an option for you. And I think humanly, this might be the shortest set of notes that we've done, I think, the entire year. So here is your job to go along with it, along with a little explanation on the other sheet that I had up there. Okay, so the simple probability, this is the homework. And I gave a little help sheet, and some of you might be wondering, okay, what do you do this for? I have learned over the past couple of years that there are not as many people that have experiences with playing cards, whether it's, go fish, poker, whatever it is, to understand what the different parts of a playing deck of cards have in it. So I decided to do this cheat sheet because there are some questions on here that have to do with playing cards. So just a quick overview. There are 52 cards in a deck of cards. There's 13 of each suit. Hearts, diamonds, spades, and clubs. And I put the colors of them on there too. So there's 13 hearts, 13 diamonds, 13 spades, 13 clubs. That adds up to 52. There are 4 of each value of card. So there's 4 2s, 4 3s, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. Okay? Because there's 13 different cards, and there's 4 of each. 13 times 4 is 52. And then the jack, queen, and king are called face cards, because sometimes you'll get a question that says, this face card, or this happens, okay? So, for instance, let me just do one with you, especially with a playing card, just to make sure we're okay. I'm going to jump down to 16. Because we've got a couple of events going on here. Okay, what's the probability of getting a red card or a spade? So it doesn't have to be both, and it can't be both because, red cards and spades aren't the same color. So my probability of getting a red card. So I'd look, and I'd say, hearts are red, and so are diamonds. And there's 13 hearts, and there's 13 diamonds, which means there's a 26 out of 52 chance that I'm going to get a red card. Now, before you reduce that, just stick with me for a second. Don't reduce it yet. Or we're going to add this second probability in because there's only one card I'm taking, or a spade. Okay, spades, there's 13 of those. And now you might see why I didn't reduce it right away, because now I got a common denominator, and that makes my life easier. Because when I have a common denominator, I can leave that alone and just add the values on the top. But before you circle that and say, ooh, that's my answer, I'm done, make sure that you take the fraction and see, does it reduce? Because if it does, I expect to see that you reduced it. Okay. And I will make one other suggestion before I get out of the way here for a bit. There's a table down below here in your last set of questions. Okay, use the table to find each probability. It would be helpful if you went to each of the rows and the columns and added the values up. So like, for instance, 54 and 49, 54 and 45 add up to 99. Or 23 and 25 add up to 48. And also do it horizontally. Okay, don't just do them vertically, because sometimes you may be asked a question, out of all the 8th graders, or out of all the people who watch under 1 hour of TV, and that way you've got that bottom number, okay, your number of possibilities to be able to put on there. So as we move forward with this tomorrow, we're going to get into what's called compound probability. What happens when there's multiple events going on at once, and how do they affect each other, and how we calculate their probability. But for today, just kind of get warmed up, kind of get yourself into this, and we'll talk a little bit more about that tomorrow.